and then выход? Или...
No.
Thanks. Okay. Last time, so we talked about the projective space bundle formula, and I kind of didn't finish the proof, but I think I said at the end that I will finish the proof, but I think the main ideas I already presented, it's basically just a collection, repeating Navier-Torrey sequence several times. Let me just write down the formula again. So here X is a smooth separated scheme over K, a field. E is some vector bundle over X, and phi is my projective bundle associated to E over X. Then I get a canonical isomorphism, which is called the projective bundle formula of the motive, or the geometric motive associated to this projective bundle. In terms of the motive of the target, just mx, but shifted and twisted appropriately. So this is not really to do with the embedding theorem. So this, the proof lives purely, it lives purely in geometric setting. So I don't need to use any kind of sheaf machinery, and in particular, I don't need to use the embedding theorem, which we did up to this point. Basically, like an application of Navier-Torrey several times, which I started in the previous lecture, but I didn't quite finish. And I think starting it up again here will just not really worth it. I think the main ideas we already saw. So let's just leave it there and move on to something new. So, wait. How do you think I should get rid of this? Maybe. Oh, okay. Thank you to all my students helping me. Okay. Now we will actually prove something that requires sheaf cohomology theory. So maybe blow up. Let's call this the blow up triangle. So the situation is as follows. I have a closed subscheme inside X, Z, everything is smooth. And then I can consider the blow up of X with respect to Z. So this is, I'm not going to repeat the definition, but if you know the definition, you already know it. But basically, this is some proj scheme over X. And the idea is usually you want to remove some singularities in X, but everything is smooth here, so that wouldn't be the motivation here. But in any case, we can still consider such a transformation, and I can complete this to fiber product, like this, and we get an induced triangle. So the statement is the motive associated to E, so M of E, just in case like M, is the map, just in case, so I'm not all lost. I guess like in the embedding theorem, I had a map, I had a square, and on the left-hand side, there was a map M, which I called, which associates somehow a motive, let's say, to each smooth separated scheme, which is a geometric guy. So the motive associated to E, which is a smooth separated scheme here, that maps to the motive M of Y. So the map E to Y induces a map from M of E to M of Y, because this is a functor. And also a map to M of Z. So I can consider in particular the sum, direct sum, because direct sums exist in this category. And this goes to M of X. The map here though is the difference. So I consider this map, so there is a map from M of Y to M of X and M of Z to M of X, but I consider the difference of that map, not the addition, so that I actually get a complex. So this is somehow the difference map. And this, so, is a distinguished triangle. So again, like if you're not comfortable with triangulated categories, just think of it as saying, like what triangle here means is that, we get a long exact sequence in cohomology, although cohomology is not defined yet, but in any case, if I take homs everywhere with respect to some other guy, then I get a long exact sequence, an honest long exact sequence. So yeah, whenever a distinguished triangle, there's this is part of the datum of a triangulated category, but more down to earth terms, like the information of this guy or any one of these three guys is determined completely by the other two guys. Think of it as like an short exact sequence. Okay, so in this case, we actually will use the embedding theorem. So I will give a sketch of proof. So this is a statement purely in the geometric setup, right? In the geometric motive, for geometric motives. So I will use the embedding theorem to transfer everything to sheaves, so I can apply sheaf cohomology. So in particular, this pullback diagram, the pullback diagram gives a complex of sheaves. So I can consider the ZTR sheaves, right? From E to Y plus Z. And this is really a complex because I define this map here to be the difference of the two maps. So I get something that composes to be zero. Now, basically, let's call this complex capital phi. So to show the proposition that I get a distinguished triangle, so by the embedding theorem, suffices to show phi is a short exact sequence. Well, maybe if I extend to 0 here. Because this triangle, or this complex, let's say, it's just coming from this sequence and then applying C star, right? I mean, by the C star was the map which was parallel to M on the other side. So to show that this is a short exact sequence, basically, I mean, the formal way of saying this is basically you want to show that, want to show that for every homotopy invariant, say complex F, then the morphisms in the complexes of Nisnowitz shears with transfers of phi to F is 0. Basically what this is saying is that like phi is the 0 object in my thing. I mean, and that's what triangles and short exact sequences are. I mean, they're just 0 objects. So if you have all maps, it's also like a property in triangulated categories that if all the maps from some complex to, or some object in your triangulated category to any other object is always 0, then the object itself is 0. And this means that this is a short exact sequence. So I don't know, like, let's say just like formalism of triangulated categories by okay. So first of all, because E to Y to X to Z is Cartesian, so by universal property of pullback diagrams, this sequence phi is left exact already. I mean, it takes a few lines to write it down, but what it's saying, what left exact here means is that, if I have a map here, what does Cartesian mean here? It means that the datum of a map from something to E is equivalent to the datum of a map from Z, a pair of maps to Z and Y, which mapped to the same thing in X. And that's just reinterpreting what left exact here means, essentially. So basically, suffices to show surjectivity of last map, of diff map, in phi. Okay, so another reduction is the following. So because this is a blow-up square, E to Z, by kind of basic properties of blow-up situations, this map E to Z is a projective space bundle so like this is just a fancy way of saying that locally this map just looks like some projective space, you know, just mapping down to T. So the upshot of this is that we get that ZTRE, well, yeah, finite correspondences like living over E in some sense are surjective over finite correspondences living over Z. So this first map, ZTRE to Z, oh, sorry, the second map, the second component, this is a surjective map. So because this is a complex, the remainder is kind of killed. There's no, it's not part of the co-kernel. So as a result, the HOM, this thing here, yeah, the HOM of phi to F, and let's assume just like F is maybe some sheaf for now, is equal to just the Nisnevich. Let's just shift to this to I. I mean, let's take an honest. I know F here is a complex, so it can be very big, but by basic arguments, you can assume that F is some sheaf concentrated in 1 degree, so shifted somewhere. So let's just take a sheaf in I. So then this basically becomes the ith Nisnevich cohomology of maybe the co-kernel of this sheaf ZTRX over ZTRY. Let me write it. Yeah, it's running out of room here. Yeah, very messy. Sorry, I've messed this up, so let me get rid of some stuff. What I meant to say was not the HI Nisnevich, but just the XI of the co-kernel of ZTRY to ZTRX, so the map that remains. With respect to F, let's say. So in the Nisnevich site. And this is like some object which Vygotsky spent some time actually calculating. I mean, this is an honest, like, you just have sheaves everywhere and you just have a higher X, so you can imagine, yeah, something that you can actually compute, but we won't do it. But in any case, I just showed the reduction of something which is something maybe manageable. But we see the power of, the embedding theorem here, where initially we had some statement living purely in the geometric motives, which is our natural setup or natural definition, and we moved everything to sheaf theoretic things. Okay. And now, like maybe for one more final application of the embedding theorem, I want to start preparing for something called like the Gaisin triangle. So this is some kind of purity result. Purity in the sense that like calculating the cohomology of some space is in some sense, the cohomology of some open subspace and the complement, as long as like the complement is pure of some dimension, constant dimension. But we need some preparation for this. So the first statement is as follows. So again, if I have my blow up square, so z to x to y to e, given a blow up square in the sense of the previous result. Assume in addition this proposition, by the way, is not Gaisin's triangle, but it's preparation for it. Assume in addition z is pure of codimension C. Then the motive attached to y, so just the blow up, is equal to the motive attached to x plus something coming from the projective part of z. So let me write it and explain the motivation. M of z of n to n. So this proposition is basically a combination of the previous result together with some projective space bundle formula happening here, because this is a projective space. This is a projective bundle, basically. So let's have a look at the proof. So by previous result, I'm not sure if I had lemma or result, maybe my previous proposition, we have a distinguished triangle. So here M of V will be, because M of V is, E to Z is some projective. So E to Z is a projective space bundle. So by projective bundle formula, the motive attached to E is equal to M of Z plus this part here. I mean, in the projective space bundle formula, I just started summing from n equals 0, but here I start from, say, n equals 1, just because I put M of Z outside. So let me get rid of this part here. And write proof instead. Yeah. So in addition, by the previous result, previous proposition, we have a triangle M of E to m of z plus m of y to m of x. So these two facts basically, so let's say 1 and 2. So 1 and 2 imply a triangle. Say this m of z cancels out somehow with m of z, so we just have this non-trivial projective part remaining. So to m of y, because m of y is the only thing that's remaining here, right? To m of x. So we already have like kind of almost what we need to show, but we need to show that this triangle splits somehow, so that there is like a morphism here, yeah, which splits this part, or a morphism here, which splits this second arrow, the first arrow. So we need to construct these splittings somehow. So it suffices to show that m of y to m of x has a canonical splitting. So this means a map in the opposite direction such that it is an identity on mx. So to do this, like there's kind of like the following trick. So we kind of we have a blow-up diagram, but we can also somehow add in an extra component and blow up along the second component. So consider the following situation. So so we have our diagram x to z to y and to e. This is our blow-up square, let's say. And now I want to consider the blow-up along, now want to consider the blow-up. I do still along z, but somehow I add z times just point, 0. And now I add x product with the affine line. I mean, somehow adding an affine line should not change anything in terms of these motives, right? Because everything, the motive of A1 is trivial. So, but we may get some extra information. So now I have a blow-up square like this. So let's call this y z times 0. This is just notation for the blow-up. Along, this is still closed inside here. And similarly, I just define by notation just e z times 0 to be this, so that this is the fiber product, a pullback. So the point of doing this is that at this stage, a loose motivation is that like adding in A1 here should not change somehow the underlying motives that we're trying to calculate, but it may give us some new information in the sense that we can of course include the 0 point, but it's also possible to include the point 1, and that gives a different map, but somehow when we look at it on the induced map on motives, these two maps should be the same because A1 is trivial. So let's see how that works. So we have kind of diagrams like this, right? Like I'm going to write it vertically. So M of E, the first kind of blow-up square, gives us a triangle like this. second, so this is kind of first blow up square. And this is the second blow up square. Say m of e z times 0. This is just notation. So at the moment, I'm not implying any relationship with the first one. M of z times 0 plus m of y times, wait, m of y, yeah, z times 0. Right? Yeah. And m of x times a1. Okay. And so there are obvious maps just by kind of, there's a map from z to z times 0, obviously, x to x times a1, and by kind of functoriality y to here. So we get maps like this. This map is induced by just the identity times 0. So identity on x times 0. And here I just get mapped by functoriality. Okay. So here is the kind of the upshot of considering or adding in this, considering the second blow-up diagram. Basically, this map here is the same as if I had just included not along the 0 point, but along just another point, 1, because m of a1 doesn't, I mean, the composition of this will just give us like the identity morphism on m of x, right? Because m of a1 is just 0. I mean, we have that, the natural projection to m of x. This is just an isomorphism. So these two maps give the same thing. On the other hand, if we look at the map id times 1, so purely as a geometric thing, x to, sorry, let me rub this out. Start on a fresh page. Yeah. On the other hand, if we have a look at this map at the level of spaces, so x to x times a1 and identity times 1. Yeah, we have this blow up z times 0 sitting above this, and somehow by properties of blow up, this map, because 1 is kind of outside the blow up along this diagram, this map lifts. So by say formal properties of blow up, maps kind of, let me just say loosely, along let's say ideals which are outside the blow up. So in this case, like 1, like in this case, 1 is outside in a loose sense, 0. The map id times 1 lifts to a map x to y, or the blow up along the 0th map. The precise statement is in, maybe you can find it in, well, you can find it in Hartshorne's book. But yeah, I mean, essentially, you can lift to the blow up as long as the map kind of is along an ideal which is invertible in the blow up. And I blew up along z times 0 here, and because I look at another line which is away from z times 0, it's z times 1, which is completely disjoint, it lifts. So here, going back to this diagram, this implies that I get a lifting here. And so I get a morphism that splits this guy here. So let me just remove this because, I mean, there's some lemma you can look in Hartshorne. So the upshot is that this morphism here, that's in my notes, I have this being 6. So morphism 6 splits. But we're still not quite there because we need to show that, yeah, m of x, I think, m of x to m of y splits, right? Yeah, something like this. This is already surjective, so we just need to show this map splits. Okay, so we need just a little bit more to maybe, so this splits also by kind of triangulated nonsense. The other one splits as well. So we need to find somehow a splitting along here, so to get a map back in the opposite direction. So, so first of all, E to Z kind of looks like the map. The projective bundle associated to the conormal sheaf of Z along X to P of Z. Oh, sorry, it's just Z. So I'm just saying that this is equal to E by blow-up formalisms. And so, similarly, this map, this second vertical map here, just this one, E Z times 0 to the closed subset, which we blew up along the second diagram. This looks like, so let me call this guy n of z, this conormal sheaf. Anyway, if you don't know the definition of conormal sheaf, it's not really important. It's just that there is some vector bundle, let's say, which makes this map E to Z look like a projective space bundle. But this map looks like P of n of Z plus O of Z, because it's somehow one more degree higher, because this 0 gives rise to O of Z. So O of Z, like coming from 0 to Z. So the upshot is that this horizontal map, let's say, yeah, 1. So that means that 1 is induced by the canonical embedding P n of z to P n of z plus O of z. And so by the projective space bundle formula, this map splits here. And so to get a splitting here, we just kind of run everything back around and get a map like this. Yeah. Let me just like end it there. But yeah, I hope that's clear that like we produced a lifting here, and then this lifting gives us a splitting of this map, which is equivalent to a splitting of this map, because this is a triangle. And then by kind of analyzing what blow up means along the closed subset where you blow up along, you get a splitting in the other direction of the horizontal map. And so combining everything together, so there's a map here, we get a map going all the way to here. So i.e. a map from here to here. So this splits this one, which gives us, yeah, a map that we wanted from m of x to m of y, let's say. That gives us the splittings, and that proves the lemma. Okay, I think now we can get close to stating Gaisin, what Gaisin sequence is, but I need one more fact. So corollary. So the reason I want to like spend like so much technicality on Gaisin things is because Gaisin, yeah, I mean, it already appears in like a tau cohomology, let's say. I mean, before even doing motives. I mean, this is like the Gaisin formalism, let's say, in motives framework, but you already see it like at a more, let's say, down-to-earth settings, just like a tau cohomology or just other cohomology theories. There's always some kind of purity result, which is this Gaisin statement. So I just wanted to kind of emphasize it in the next, like, whatever, 10 minutes until we move on to another topic. So one more corollary before we state Gaisin's theorem is the following. So in this diagram, or the previous lemma, so given, say, a blow-up triangle, z to x, y to e, a blow-up square, like in previous propositions. There exists a morphism, let's say canonical, non-zero morphism, which let's call g of z from m of x to m of z, c, twisted by c and shifted by 2c. Like this morphism is required to state the Gaisin triangle. So like, sorry for like the randomness of this, but if you just bear with me for one more, well, like this is the last, let's say, random result before the Gaisin statement. So sketch. Okay, so if we just look at this diagram again, so there are two morphisms. There are actually two morphisms. From m of x to this thing. So m of x to m of z times 0 plus m of, or the motive of y, or the blow up along z times 0 when we included a1. So the first, one morphism we constructed, so it's the lifting. So lifting of blow up. So like Hartshorn. And another morphism which comes from the splitting of, say, this morphism here, let's call it 5, which was the morphism that we split in the proposition. So these two morphisms turn out not to be the same. But in any case, we can look, consider the difference of these two morphisms. And the difference is certainly 0 on this target here. I mean, if we consider the the composition of the difference with 6, it becomes 0 here. So that means that that difference, let's call this morphism, let's say, what do I have here? F maybe, or F. So this implies that, let me, sorry, I will rub this out. Okay, I would like to keep this diagram, or, So this implies that's F. So our difference morphism, which goes from, I just remind you, m of x to m of z, the locus along where we blow up when we include a1, and the motive attached to the actual blow up of the second blow up, lifts to a morphism let's say m of x to the very top guy here, because it's 0 here, so it must be okay to lift it here. But as I kind of mentioned in the previous results, in the previous proof, this guy is just the projective space bundle of this co-normal sheaf attached to Z plus O of Z. And so by the projective bundle formula, formula. This is equal to the sum of the motive of m of z twisted by n, sorry, where n ranges from n equals 0 to c. And so we get our map from m of x to m of z c to c by projection. Okay, good. So I'm not like claiming many properties about this map, but anyway, we have this map, and if you study it a bit more, you see that it's not zero, and it's the right map to consider in the following setup, which I now state. So theorem, the Gaisin distinguished triangle. So yeah, I will use the embedding theorem here, and in the embedding theorem, I've been a bit loose with like the previous propositions where I used embedding theorem, but the embedding theorem requires that K is perfect. So if in particular, K admits some resolution of singularities. But when I proved the embedding theorem, I don't think I made that really clear as to why K needs to be perfect. So sorry about that. But it essentially comes from the fact that when we compared some Holmes to Nisnevich cohomology, and this comparison only works when K is perfect. But I think I skipped over that and I didn't state it clearly. But anyway, the assumption is K is perfect due to embedding theorem. And maybe in some other theorems I've been not stating it explicitly. So let z to x be some closed codimension C embedding of smoothly separated schemes. Then I have the complement, which is open. And so the statement is that then there is a distinguished triangle so the point is the following, we want to study the motive mx, which is clear. I mean, we always want to study mx, and we can study it along smaller pieces. So on the one hand, we have a smaller piece associated to x minus z. So there is this map here induced by J. And on the other hand, there is a map here coming from the previous corollary. So there's this map, which I denoted by G of Z, I guess, of M of Z, C to C. Okay. So this basically, says that we can study this object, which contains some deep cohomological invariance or information of X in terms of smaller pieces, here and here. And I think I won't prove this. I mean, it's in lecture notes if you're interested, but I think the main ideas are already kind of coming from the previous proposition in some sense. and we also should move on to other things. But let me state like one interesting corollary of this. So this category like of geometric motifs, right? Yeah, it was kind of defined roughly as something on smooth separated schemes. So like the bounded homotopy complexes of smooth separated schemes. Well, finite correspondences of such guys. Anyway, you see that this is a lot more than just like projective smooth varieties. But, so using resolution of singularities, this bigger category, DM geometric, is kind of generated by objects M of x, where x is smooth projective. So the way, so again, I just want to emphasize that, like, by first of all, what does generated mean here? It means that I can consider like all motifs attached to smooth projective guys, and then I consider, you know, all triangles formed by such motifs, and then I consider shifts of such things as well, and summands as well. So to get a huge triangulated category, and this will be the same as this. So somehow, these smooth projective guys somehow see through some, nonetheless complicated operations in a triangulated category, the cohomology of smooth separated schemes. It doesn't mean that like cohomology of smooth separated schemes is kind of trivial now because we kind of understand smooth projective guys, but because the complex and the operations to generate all the objects from this is still nonetheless complicated from a cohomological perspective. But the way to achieve this, I think, is as follows. So like you can take so how roughly so you can take x just smooth separated, and then you can, by resolution of singularities, so by Heronika's resolution of singularities, let's say, you can embed this into a smooth projective guy. Let's say, y. And then I have like by Gaisin, like M of y, which is smooth projective, and it goes into M of x somehow. Sorry, there's a map from M of y to M of x, C of 2C. Somehow this thing will be the complement, so given by Z, so complement given by Z, which is some normal crossing divisors of pure codimension, of some pure codimension. So you end up getting, well, using the Gaisin sequence, Gaisin triangle gives you something mx in terms of M of y and something smaller, and then you already know y is smooth projective, so this is okay. Z may not be, but it has some smaller dimension, and then you can use some induction argument to prove that, that Z is also generated by smooth projective guys, and so M of x is as well. because these two guys are. So that's the rough idea. Okay. Let me now start kind of the next topic. So at this point, we have like a few kind of categories that we have considered. So in the first half of the lectures, we had like the category of Grothendieck motives, right? Of up to rational equivalence. So these are Grothendieck's. Smooth projective guys. And recently, like in the last few lectures, we've considered like motives in the derived setup, so not dropping in particular the projectivity assumption. So we have on the one hand this geometric motives. And we also kind of, to prove things here, we considered some sheaf machinery version of it, so DM, and in particular we chose the Nisnevich kind of topology. So this will be some kind of sheaf version, or sheaf transfer version. So by the embedding theorem, we know this kind of leaves it like this. So it's still kind of a natural question as to like where exactly this guy fits in. So I think the next two lectures we will spend like some time like discussing this, and of course like this will be true. And so yeah, the way, yeah, there are several kind of ways to prove this. So, but our approach will be, we'll use something called equidimensional cycles. So, equidimensional cycles to show Grothendieck motives. Sit fully faithfully. In geometric motives. And along the way, so like this will involve studying like, I mean, I'm claiming some fully faithfulness here, so we'll need to study like homomorphism spaces or homomorphism sets of these two categories. And homomorphism sets in the derived setting is basically some higher X or some cohomology or something that's called motivic cohomology. So we need to, like, before we get there, we need to look at motivic cohomology. Which is basically studying Hom sets in these things. And like historically in the literature, like motivic cohomology was defined before these things were well defined, these categories. And they were defined through something called like Bloch-Higher-Chow groups. So now, like just for historical reasons, I want to define what Bloch-Higher-Chow groups are, connected to motivic cohomology in this kind of modern, not the modern, but like in Vygotsky's framework. and then we'll look at like some properties of motivic cohomology and eventually massage out that Grothendieck's motives sit fully faithfully in here. So the pathway of like this very natural question is studying motivic cohomology, and in particular using this equidimensional cycles as an intermediary object. So at first point, like let's look at Bloch's higher Chow groups, which is kind of more the first definition of motivic cohomology. Okay, so I've been saying motivic cohomology several times, so let me just at least give a definition before I go into Bloch's higher Chow groups. So definition of motivic cohomology. I mean, I could have defined it a while ago, but maybe why the definition is not so illuminating. So the notation is as follows. So like, I want to consider the P, something like the P cohomology of X, where X is let's say just a smooth separated scheme for now, in coefficients. So my basic motive is something like Z twisted, right? So I twist by Q. And like cohomology is nothing but homology, Hom sets in the derived category. So this should just be a natural definition, which is which holds in kind of almost all cohomology setups. I take the homomorphisms in my category DM geometric motives, say effective for now, of the motive morphisms from the motive attached to X, and Z of Q, but shifted by P. So it's like some higher X. And maybe just so like this definition is not going completely out of control, I should assume for now like Q is positive, because I'm working with effective guys. So Z of -1 is not like in this category. I mean, I would need to invert it, and it's also a delicate question whether like, I mean, I could write this down for Q any integer. In that case, I would need to delete effective, but it's actually a delicate question whether like DM, so geometric motives, effective, with the Z1 inverted, whether this actually sits fully faithfully in geometric motives. So this is the category with Z1 inverted, which I roughly defined in the first lecture. Anyway, let's just for now consider Q greater than 0 so that the definition makes sense. Okay, so Bloch's higher Chow groups will... So what are Chow groups? Chow groups are the homomorphism sets in kind of Grothendieck motives, right? And here we have homomorphism sets between, well, not just Grothendieck motives, but some motives which are not projective, but let's just forget about that technicality. But more importantly, we have homomorphisms between some kind of, in some derived category, first of all. The Grothendieck motives was just a normal category, not derived. And so there's some higher shifts going on here, or higher X's. So Bloch's higher Chow groups is just kind of the analog of Chow groups meant to capture these homomorphisms, these higher Hom sets, which are coming from this shift. So I think we just maybe state the definition and state some properties. I'm not sure how much time we have, but Bloch's, at least this was Bloch's idea. So these higher Chow groups should be some derived version of Chow groups, which are meant to capture these Hom sets. Although at the time when Bloch defined this, these things were not properly defined. But anyway, he guessed the right definition somehow. Z, so R, X, M. So here R, M, say are positive integers, and X, a smooth separated scheme, but can also be just finite type maybe, or just finite type. Over K. So this will be the free abelian group of irreducible closed subsets of X times delta M. Remember, this delta M was nothing but affine space in dimension M, but I can be defined in some way so that we get a cochain complex coming from the previous lecture. So if I just define it, so this certainly is some kind of higher analog where I just look at cycles living in this product, but cycles, just having cycles without any properties, is just going to be too crazy. So we need some kind of something so that we can take compositions or intersection products. So somehow the minimal thing you can say is the following. So it's these cycles which intersect all faces X. So the faces are just given by setting some coordinates to 0. So delta J, so here for J less than M, which intersect all faces properly. So it turns out that by adding this properly condition, we recall that properly is very heavily connected to whether we can make intersection products and whether we can define correspondences or composition of correspondences which involve an intersection product. And this is kind of the most general thing you can say. It certainly includes finite correspondences and things like this, which make compositions work, but just by setting in proper, prop intersect properly, which is kind of defined briefly in some very early lectures. Anyway, it's a technical condition which is the minimal thing you can say, you need to say, so that these kind of things sit together well in the following sense, which I'm about to write down. So, so these are this ZRXM are these things, and we now get some cochain complex similar to the Suslin complex. So these the face maps say delta I of setting some ith component to 0, we get a map like this. Defines a pullback map let me write it in the next page. So, just so not everything is too abstract here, I mean, pullback of algebraic cycles, you can define it, if the pullback was along some smooth or flat map, there would be no issue. You can just define it as literally the inverse image along your map. But this is a closed immersion, and it's, yeah, not smooth, typically. And so pullback will be defined through some intersection product, typically. And it turns out that, like, by adding this condition, which intersects all faces properly, this pullback is actually well defined. So, like, in some very early lectures, I mentioned, like, in an exercise that, like, one can write down, like, some candidate. So one can always write down a candidate definition of pullback of cycles as an intersection product, as some intersection product. But the issue, again, like in all things, like, I mean, hence, like, the importance of the moving lever and things like this is that this intersection product is not always well defined. So not always well defined. And even in the smooth projective case, like, it's not even well defined there, but we have, like, this miracle moving lever, let's say. And in the smooth separated case, which is the second half of the lectures that we've been dealing with, we deal with finite correspondences, so this is well defined. And so anyway, in this case, it's well defined because is well defined due to, say, let's call this condition star, so star, so by star. It's not, like, easy to, I mean, it's like a page of like technical write-up, let's say, but at least the intuition, that's the idea. So we have these pullback maps, and so these basically, like, by considering the complex, let's say 0 and then ZR x of 0 and then ZR x of 1 and ZR x of 2 and so on, where morphisms are given by some alternating sum, the usual thing, just so that we get a complex of these pullback maps. This is the complex because I've made the morphisms this alternating sum. I mean, one needs to check this. Now blocks, sorry, it's a bit of a long definition, I guess. Blocks higher Chow groups are defined to be the homology of this map. So CH R X M is the mth homology of this complex of Z R X. And let me just finish by saying that CH of R X of 0, so the cohomology at this guy is equal to, I guess, check the usual chow ring or group at the rth codimension. Okay, let me finish there for today. I always don't know what to press. Sorry.